In this video, we present contrastive analysis for scatterplot-based representations of dimensionality reduction. Here is our agenda. We use high-dimensional data analysis most of the time when working with data. We often visualize high-dimensional data using scatterplot after dimensionality reduction. For example, if I have high-dimensional data, I can use a DR technique to project it into R2. Using this projection, I can formalize a few questions like what makes spondylolysis patients so different from normal and hernia patients? To answer these questions, we can use statistical charts to visualize attribute variability and quality metrics that offer a level of interpretability but are not enough to explain cluster differentiation. We can use PCA to find the most important features, but since PCA tends to focus on global information, it makes difficult to understand the difference among clusters. Or we can use CCPCA, but we are unable to use on thousands of dimensions. So let's define the numerical component of our approach, C expression. Let's focus on F2 and cluster 0. We take the distribution of F2 for cluster 0 and the remaining of the dataset and ask the question how much these distributions differ. We use t-test to answer this question, which returns t-score and p-value. T-score will measure the difference between the distribution of F2 for cluster 0 and the distribution for the remaining of the dataset, and p-value will tell us how much trustful the result is. We repeat for every feature and for every cluster, and for each cluster, if we order the features based on t-score, we will have on top the most defining features. Here we show all the components of our approach. We have the scatterplot view, the summary view, the scatterplot layout after interaction with the summary view, and the heat map view to provide an overview of the most defining terms for each component. When users click on distribution plot, they can visualize the distribution of feature values on the scatter plot, and if more than one distribution plot is clicked, we divide the scatter plot representation into cells to encode all the feature values. For the use case, we use a tweet dataset about COVID-19 symptoms retrieved in São Paulo State, Brazil. We want to understand how the symptoms differ across the state and what are the unique characteristics. So we take the tweets and use the BERT language model to embed the dataset and use the embeddings to project it onto R2. Let's start our analysis on dark allergic cluster. Here, the tweets talk about shortness of breath, anxiety, and chest. Shortness of breath is a severe COVID-19 symptom. We also see anxiety in this cluster, which have grown in the pandemic times. Now let's look at the red cluster. You can see the most defining terms are coryza, stop, risk, mask, worry, and so on, such as fever and pain. Here, tweets are mainly talking about the worrying of wearing or not wearing masks, or worrying about other symptoms that may or may not be COVID-19. Now we have some discussions about the work. The cell-based encoding reduces change blindness because we can visualize various features values on the scatter plot at the same time. R2 offers focus plus context interaction to deal with high-dimensional datasets. And when analyzing different VR techniques, if the clusters are the same, the results will be the same. Then we recommend analyzing at most 5 feature values on the scatterplot representations because of visual scalability. There are more on the paper and the extended video. We recommend you to take a look at them. Thank you.